So Newton's third law of motion. So the first law is an object at rest will stay at rest, an object in motion will stay in motion unless acted on by some unbalanced force. Newton's second law is the equation force is equal to mass times acceleration. Newton's third law, a lot of times you might, when I say this, this might jog some memories, like for every action there's an equal and opposite reaction. Heard that? Junior high, maybe sometime, physical science. Okay. That's a good memory, something to jog the memory, but I really don't like that definition because it makes us think of things that aren't Newton's third law. So like what goes up must come down. Well, that's an equal and opposite reaction, right? It's like, yeah, but that's definitely not Newton's third law. If I hit you, you hit me back. Equal and opposite reaction. Yes, but not Newton's third law. Okay, so here's a better definition of Newton's third law. If object A exerts a force on object B, then object B exerts, and object B simultaneously exerts an equal force, simultaneously exerts an equal force back on object A in the opposite direction. If object A exerts a force on object B, and object B simultaneously exerts an equal force back on object A in the opposite direction. Object A exerts a force on object B, and object B simultaneously exerts an equal force back on object A in the opposite direction. Definitely a mouthful. Not as easy to remember as for every action there is an equal and opposite reaction. You can kind of see where that comes from, but this is definitely more complete. Good with that? Okay. So the rest of the day is just unpacking this. All right, so some examples. You kick a ball. So in that process, you exert a force on the ball. So your foot exerts a force on the ball. So Newton's third law would say that, well, if your foot exerts a force on the ball, then what else is true? Yep, there's a force on your foot from the ball with the equal force in the opposite direction. Now you might be thinking to yourself, that's stupid. Like the foot exerted the force, the ball did not. The ball is just sitting there. The ball is the victim. Like, how can the ball exert a force on your foot? Well, let's pretend you missed the ball. You whiffed, you kicked, and you missed. Would you know you missed? Yes, because you're expecting to feel what? The ball, feeling a force on your foot from the ball. Does that make sense? Okay. If you're pushing on a refrigerator, the refrigerator is pushing back on you. So there's a force on the person from the refrigerator. With the same amount of force that you're putting on the refrigerator. That seems kind of weird. But let's pretend we just made the refrigerator disappear like that. What would happen to you? You'd be like, whoa! Oh. So you're expecting that force back on you. Okay? And the reason there is a force is because, well, the refrigerator has inertia. Good with that. It doesn't want to move. Let's say it starts to move. That's fine. It wants to maintain whatever speed it has. And you're like, nope, keep going. Okay? If we were to draw a free body diagram of the chandelier, we'd say there's a force of tension up. Okay? But let's take it from the chain's point of view. What is the chain experience? The chain is like, oh my goodness, the chandelier is so heavy. If you were a link in the chain, you'd be stretched. There'd be tension. Does that make sense? Okay. This last one's really weird. So, a raindrop, free body diagram, force of gravity. We're good with that. But what object causes gravity? What object is responsible for creating that force? Okay, something that we really haven't talked about. The answer's up on the board. Your Earth. Okay, and we'll talk about this next semester when we start talking about planets and such. But the fact that the Earth is so massive, that's what creates gravity. Okay, so there's a force of gravity on the raindrop from the Earth. So based off of Newton's third law, what has to be true? There's a force of gravity on the Earth from the what? Raindrop. Oops. Acting which way? Up. Mr. Smiley, your Thanksgiving break was really too long, I think. Like, force of gravity up? Like, what? So Newton's third law says if an object A exerts a force on object B, then object B exerts an equal force back on object A in the opposite direction. The same amount of force. Whoa, that's weird. Okay, so wait a minute. So if I jump, if I jump, gravity's like pulling me down. We're good with that. Okay, I experienced an acceleration of 9.8 meters per second squared downward. So are you saying that the Earth also is accelerating up towards me at 9.8 meters per second squared? You guys feel that? Did the whole Earth like come up towards you like at 9.8 meters per second squared? Quit jumping, man. Seriously, you're ah. Why not? We did. So, well, there is a force of gravity on me from the Earth, but there's also a force of gravity on the Earth from me pulling it this way. And usually, but in this scenario, I'm going to say I'm separate from the Earth. Any other guesses? These are good guesses. Yes. The Earth has just so much more mass than I do. It experiences the same force, but my acceleration is so much bigger because my mass is so much smaller. Okay. Some people are like, wait a minute, Mr. Smiley. Are you saying that if like we got all the people on Earth together, like in one spot, and we like all jump to the same time, we could like alter the orbit of the Earth? Is there? So let's do a quick little approximation exercise. Okay. So we're at 8 billion people, right, on Earth. Let's just round that up to 10 billion just to make math easier. Okay. So just add 2 more billion people. That's fine. Okay. So a million is 6 zeros. A billion is 9 zeros. 10 billion would be 10 zeros. Good with that? Okay. Let's say that every person was 100 kilograms. That's like 212 pounds. It's a big baby. Okay. But let's just pretend. Okay. So the mass of all humankind is, so we had 10 zeros. Now we have 12 zeros. Good with that? Guess how many zeros the Earth has? 24 zeros. You're not going to make the Earth changes. But if we had like all the elephants and the whales and we like no, it doesn't. No, just like nothing. Good with that. So no worries. We're not going to change the Earth's orbit. You can sleep tonight. All right. Oh, I killed my clicker thing. Oh, I did kill it. Stink. Come to me. Oh, death. Happens to everything at some point. Sad day. All right. So here's some characteristics of Newton's third law, sometimes called action-reaction forces, force pairs. So they always act. They always have the same magnitude. So always have the same strength. They always act in opposite directions. They always act simultaneously. They always act on different objects, and they never cancel each other out. So these first four are kind of captured in that definition. That last one, though, they never cancel each other out. That is a consequence of the fact that that never acts on the same object. It acts on two different objects. And we will, each one of these will like demonstrate throughout the day. Okay. Good with that? All right. So here's your first scenario. You got two blocks they're on a rough surface. You're pushing block A, which is the more massive one, causing them to speed up. So the question is, which block exerts more force on the other block? How does the magnitude of that block A exerts on block B compared to the magnitude of force that block B exerts on block A? Tell your neighbor. Correct answer is D, because of Newton's third law. Same force. Okay. Same scenario, different question. Talk to your neighbor. Correct answer is D, dangerous dinosaurs. Okay, what do I mean by that? So if we drew the free body diagram of both of these, on B, we would have force of gravity on B. We'd have a normal force on B. We'd have, we'll call this a normal force on B from A. And we'd have a force of friction on B. And if we did the free body diagram for block A, we'd have its own force of gravity, its own normal force. You have applied force from the hand. You'd have friction, oops, on A, but you'd also have this normal force on A from B. Which two forces demonstrate Newton's third law? That one and this one. Object A exerts a force on object B. Object B exerts an equal force back on object A. Okay. Now, this force and this force cannot cancel each other out because they're acting on two different objects. This force can cancel out this force because they're acting on the same object. But this force and this force cannot cancel each other out because they're acting on two different objects. Cool with that? Does that make sense? That characteristic can't cancel each other out because they act on two different objects. Okay, so on this this next slide, I've changed the scenario. I swapped A and B around in the order, but I'm pushing on A. Sorry, I'm pushing on B. Correct answer is everybody okay with D? Newton's third law. Same force. Okay. Tell your neighbor what you think. Okay. Correct answer is C. When I was in your shoes, I could tell the teacher exactly what they wanted to hear, and we're like, "Yep, C, same, Newton's third law," but I didn't really believe it. I'd be like, "Okay, whatever. If they say so, I'm going to say that to get the A," but I'm not really. Yeah, until I saw this demonstration. So what I have are two carts. And they're going to have force probes on them to measure how much force is being delivered, experienced. Okay. Okay. Oh, that was. All right. So what you're going to see is this. So this is the force on one. This is the force on the other. Nice. Okay. So what I want to do is I'm going to go through a series of interactions. I'm going to do a head-on collision. Oh, we need a Mack truck. Mack truck. Volkswagen Bug. Is that right? Can't remember which one was which. Oh, well, whatever. Okay. So we're going to do a head-on collision. Boom. We're going to do a rear end. Boom. We're going to do a rear end. Boom. We're going to push. We're going to push. We're going to push, push, push. Any interaction that I could come up with. Does that make sense? Okay. We're going to see what the forces look like on these things. Okay. So Well, this is being a little difficult. Let's try that again. That's better. All right, here we go. Head-on collision, boom. Rear end, pushing, push, 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 push. Do you see that? Like, that is pretty phenomenal. Ignore that as it being weird. Same force, the exact same time, simultaneously. It's like a butterfly. Okay. This demo, when I saw it, sealed the deal for me. I'm like, look at that. It is exactly the same every time. Doesn't matter what happened. Same force, same time, simultaneously, opposite directions. Good with that? Questions there? All right. So back to this. Experience the same force. So C, like you said. So then a follow-up question is this. Tell your neighbor. Tell them why you think so. Okay. Which one experienced greater acceleration? A. Why? Has less mass. Both experienced the same force. But the Volkswagen Bug had a small mass, therefore it experienced a huge acceleration. Versus the Mack truck had a huge mass, therefore has a lot of inertia. Experienced a little acceleration. Okay? So when this happened, it was like, okay, the Volkswagen Bug changed its direction. Versus the Mack truck was like, ooh, I think I hit something. Does that make sense? So they experience the same force, they just react, they respond differently to that force based upon the mass of the object. Which one has more or less inertia? Good with that? You know what? Funny thing is, I made this question probably 15 plus years ago. C is still true. Right, but the real answer is, okay, which experiences a greater force, the bullet or the gun? Or the same? Which one experiences more force? Tell your neighbor. Okay. Which one experiences more force? The same. So why does the bullet go flying and the gun? Okay, so if you ever shot a gun or you've seen movies of the gun, when the gun is shot, there's a kickback. There's like a, okay? That's how the gun responds to that force. Why does the bullet go flying and the gun doesn't? Because the gun is way more massive. Well, this is true. But if you held a bullet in place, okay, so if you had a lightweight gun, it's probably going to be 2 fatalities. Does that make sense? Like it's, you get, good at that? Oops, wrong way. Correct answer is C, the same. So how does the board break? So as the hand hits the board, the force on the board from the hand is the same as the force the hand experiences from the board. But the force that the board experiences from the hand is greater than the molecular bonds can handle. And so that is why it breaks. Does that make sense? It's the thing like the board can't handle that force. The molecular bonds of the board can't handle that strength of force, and therefore it breaks. Good with that? Last question. Have a conversation. And tell them why you think so. What do you say? Why is it false? Do they have equal amount of force? Yes. Are they acting in opposite directions? Yes. So why aren't they Newton's third law? Acting on one object. These are canceling each other out. Okay. There's a normal force on the book from what object? The table. So Newton's third law would say there's a force on the table from the book. That would be Newton's third law. There's a force of gravity on the book from the what? Earth. Therefore, Newton's third law, force pair, would be a force of gravity on the earth from the book. That would be Newton's third law. Go to that. Okay. You have a pre-quiz for tomorrow.